Okay, hello everyone. Welcome to the morning session. And we next will have two plenary talks. The first talk is by Professor Zuoqiang Shi from Tsinghua University, and he will talk about no-local diffusion modules with Dirichlet boundary condition. Let's welcome.
Uh, Thank you for the introduction, and thank you for so many people come to my talk. And today I will talk about non-local diffusion models with Dirichlet boundary condition. Maybe many people know Dirichlet boundary condition. It's very familiar to you. It's a very widely used boundary condition in PDE. But maybe not many of you are familiar with the non-local diffusion model, although actually, today this talk is closely related to two frontier science award papers. One is the paper, sorry, oh, okay. One is a paper of the numerical method for non-local and fractional models, which is written by Professor Zhou Zhi. Actually, Professor Zhou Zhi also gave a talk on Monday. He gave a very good introduction to non-local models. And also, our talk today is also related to another best paper in the scientific computing category, which is written by Professor Zhao. He will give a talk on the solving partial differential equations on point cloud tomorrow. And because a non-local model actually, in some sense, can give a numerical method to solve PDEs on point cloud. So it's also related to the numerical method on point cloud. And so first, I will give a brief introduction to the non-local models. Non-local models, as its name, is not local models. So what is a local models? Local models is actually partial differential equations. Due to this theorem, we know that the PDE models are local models and the only ones. So the local models are actually partial differential equation models because we know that the differential operators are local operators. And so as its name, the non-local models is not a PDE models, but it's so wide. It's very wide. In this talk, we will focus on the non-local models which can be written in this integral form, and the kernel has finite interaction ranks delta. The support, which means that the support of this kernel is bounded in this area. And one example, more specifically, we will focus on the so-called non-local diffusion operator, which means that here the kernel function is given in this form. Here R is a one-dimensional function, which means that the kernel function is a radiosymmetric. And because we know we can prove that, people can prove that as delta goes to 0, if the kernel is in this form, then this non-local operator converge to, in some sense, converge to the Laplacian operator. So we also call this operator, the non-local operator with this kind of kernel, we call it a non-local diffusion operator or non-local Laplacian operator. This is the non-local diffusion operators we will talk about in this talk. And as mentioned in Professor Zhou's talk on Monday, non-local models has many applications. This is one slide I borrowed from Professor Qiangdu's talk. He mentioned that, for example, the non-local models has an important application in paradynamics. The paradynamics is, roughly speaking, is that for the solid mechanics, we know that solid mechanics has very beautiful PDE models to describe it. But when the singularity emerge, for example, the material crack, then the PDE models is failed to describe the correction, the propagation of the correction. Then we need to use the so-called non-local models, which is the paradynamics. Actually, in some sense, when the singularity emerge, the PDE models, the local models often fails. For example, if we maybe some people are very familiar with the conservation laws. When the shock, when the shock wave format, then the PD models fails. We need to go back to so-called weak solutions. The weak solutions, in some sense, can be seen as non-local models because it's in the integral form, right? So the other application is the numerical method to solve meshless numerical method to solve partial differential equations. One example is the so-called smoothed particle hydrodynamics. In this method, we use integral formula to approximate the differential operator. So this is also closely related to the non-local models. And the non-local models are also related to the traffic flow. And more importantly, it can describe a so-called subnormal diffusion process. Actually, Professor Zhou gave a very good introduction to this phenomenon in his talk. And our motivation, the original motivation to study the non-local model is a so-called semi-supervised learning problem. In semi-supervised learning is an important topic in machine learning problems. In some sense, semi-supervised learning can be formulated as interpolation in high-dimensional point cloud. It's the typical semi-supervised learning is that we have a bunch of points in high-dimensional space, and we want to know a function on this point cloud, but we only know the value of this function on partial points, not in the whole points. In partial points, in these points, we know the value of this function, and we want to know the value of this function over the whole point cloud. And this is a typical formulation of the semi-supervised learning. And one approach that this is, in some sense, is an interpolation problem, right? But this is an interpolation in high-dimensional unstructured point cloud. One approach is that we just want to find the smoothest functions to interpolate the given points. And we need a measurement of the smoothness. One simplest measurement of the smoothness is the L2 norm of the gradient of this function. If you use this L2 norm of the gradient as a measurement of the smoothness, then you can write that semi-supervised learning problem in this form, in this optimization problem. This optimization problem is a very classical problem. We know that using a standard variational approach, this problem can be solved by the solution of this Laplacian equations, right? So, and the constraint is this G is the values given in that labeled points. So this kind of labeled points can be seen as the Dirichlet boundary conditions. In some sense, it's a Dirichlet boundary condition. So in the semi-supervised learning problem, we can get this. Then we transfer to this Laplacian equations on point cloud with Dirichlet boundary conditions. And how to solve this problem? If the Laplacian equation is in the Euclidean space, two-dimensional, three-dimensional Euclidean space is a very classical problem. We have many methods to solve it. For example, find the difference, find element, boundary integral, or many different methods we can solve it. But now we need to solve it in high-dimensional unstructured point cloud. It's not so easy. One approach is that so-called graph Laplacian, which is widely used in machine learning community. They just in the graph Laplacian, they just use this integral operator to approximate the original Laplacian operator. then you get this non-local diffusion models. But in that in this method, they impose the Dirichlet boundary condition directly without any modification. But if you have this integral equation, want to solve this integral equation, but only impose this Dirichlet boundary condition directly, it does not make sense. Because if it is a real boundary condition, then this boundary condition is only on a mass 0 set. Then this here, it does not have any effect on the integral equations, right? So because we know that the integral over a mass 0 set is also 0. So of course, however, in machine learning community, it just discretize this integral equation directly, replace the integral by summation directly. Then you get this linear systems. Then you can solve this linear system to get the solution of the semi-supervised learning. This is a tall example in one-dimensional case, very tall example, in this interval 0 to 2, with 6 labeled points. And we can see that on these labeled points, in some sense, this is a boundary condition. But on the boundary, the solution we get from the graph Laplacian has jumps, which means that this boundary condition is not correctly imposed. So this is some kind of motivation, the other motivation of the non-local models. So now let's go to the mathematical problems. Now in this talk, we will focus on this classical Poisson equation with Dirichlet boundary conditions. And we want to find the non-local counterpart of this problem. Okay, how to do that? Actually, our approach, sorry, it has some delay. Okay, actually, our approach is based on this integral approximation. The whole talk is based on this integral approximation. Actually, this is a Laplacian operator, and R bar is one kernel function. A given kernel function R is another kernel function. It has a this relationship. Actually, R bar is a primitive function of R, and we can get this integral approximation as delta goes to 0. This integral operator will converge to this one. As we can see that the first line is just the integral operator used in the graph Laplacian. But one important thing is that when there is a boundary, we also have this boundary term. Here is a normal derivative of the function u. Which means that if you want to impose a boundary condition, the normal boundary condition is natural in non-local model. If you know the normal derivatives, you can replace these normal derivatives directly. Then you can get integral equations, which is the non-local model for Neumann boundary conditions, very natural. But for Dirichlet boundary condition, it's not so natural because we do not know these normal derivatives. But we cannot drop this term, boundary term directly, because this boundary term is actually not small. Okay. The proof of this this approximation is actually very straightforward. It's just based on the integration by part and Taylor's expansion. I just give a very simple derivation analysis of this integral approximation in the Euclidean space. It also holds on the smooth manifold, but in the manifold, the notation is very complicated. So I just use the Euclidean space to show the sketch of the analysis. And First, we multiply this kernel function and do integration over the domain omega, and do integration by part to get this one. It's very easy. And the first term here, the gradient of this kernel function, we just use the relation between R bar and R. Actually, the derivative of R bar is R. So we get this one, this formula. And we want to the goals of this derivation is to remove all the differential operators in this formula. Here is the only differential operators we have. We want to remove this first order derivative. One natural way is that using the Taylor expansion. This term can be approximated by this difference using the Taylor expansion. It is just the linear term, the first term in the Taylor expansion, right? So one natural way is to just replace this gradient by this difference. Then we can remove the differential operators. But this approximation does not work because this is an approximation with some error. We know that based on the Taylor expansion, we know that the error term is of the order of x minus y squared. But in front of this integral, there is a delta square here. We know that the x minus y square has the same order with delta square. So the error, if we use this approximation, the error is of order 1. So you cannot use this approximation directly. Then the idea is very, very simple. We just include more terms in the Taylor expansion. We include the second order term in this Taylor expansion. And then we can get this approximation. So we in this Taylor expansion, we just include this second order term. And then the error is this type. And this order is small. It's an order of delta, so it is small as delta goes to 0. And but there is another problem. Here we want to remove the first order derivative, but we introduce the second order derivative. Right. So, but fortunately, this second order derivatives can be eliminated by some derivation. So let's look at this second order derivative term. We can rewrite, first we rewrite this one, this term. We can absorb the one difference, 1x minus y with this kernel function and get this term. It can be written as a derivative of this kernel function, right? And then we do integration by part. To remove this differential operator onto other terms, we get these 3 terms. The first one is we put this differential operators on this term. This term just gave us the Laplacian operator, actually. And the second term, we put this differential operators on this one. Then we get this term. If we assume that U is smooth enough, for example, in C3 space, and this term is actually small because we have an x minus y here. This term gave us the order of delta. And the last one is the boundary term. And we keep it here, which is the boundary term. Okay, combine all this. Actually, this term actually is the same with the original term in the left-hand side. But now we have 1/2 in front of this term. So using this simple derivation, we can get this integral approximation. And the error term is actually of this form, this boundary term. and this order of delta term. Actually, this boundary term is not small near the boundary. There is x minus y here, which seems to be small. But the integration is over the boundary, which is one dimension less than the original domain. And the integration on the boundary, the integration of this kernel function over the boundary is actually of the order of 1 over delta. So near the boundary, this term is actually of the order 1. It is not small. But fortunately, its support is in a small layer, very narrow layer adjacent to a boundary. So this term, the L-infinity norm of this term is not small. It's of order 1. But L2 norm is small. It's of the square root of delta. So this integral expression actually has this kind of structure. It is of the order of delta over the interior area, and in a small layer adjacent to the boundary, it is of the order 1. Okay. So this is the derivation of this integral approximation. And now we can use that integral approximation to develop the nonlocal models of Dirichlet boundary conditions. The first idea is that the so-called volume constraint, which was proposed by Professor Qiang Du. And the idea is like this. It just in volume constraint, it just extends the boundary condition from the boundary to a small layer adjacent to the boundary. So it is called a volume constraint. It is not a constraint on the boundary. It is constraint on the volume. This is a very natural idea. The width of the layer of this layer is associated with the width of the kernel, the support of the kernel. Which means that then based on this integral approximation, this term, this boundary term, also the support of this boundary term is also in a small layer adjacent to the boundary. If we put x is in the interior area, then this term vanish. Is 0, which is 0. So if we extend the boundary condition to a small layer adjacent to the boundary, we know that we can only put here the x in the interior area because we know that u is the value of u is in this small layer. But in the interior area, this term just vanishes. So based on this observation, we can get this nonlocal models with volume constraint. Here, V delta is just a small layer adjacent to the boundary. And we can prove that this nonlocal model, as delta goes to 0, it converges to the solution of the counterpart local model in this rate, square root of delta, which is not very hard. But we can only prove that it converges in the square root of delta. The rate is like this. Okay, this is the first model, the volume constraint model. However, the volume constraint is actually, in the volume constraint, we need to do extension, some kind of extension from the boundary to a small area. For 0 or constant boundary conditions, it's easier to do that. But for general boundary conditions, it's not trivial to do this kind of extension, right? So is there any other approach to impose the Dirichlet boundary conditions? This is another model we will introduce. The idea is also very simple. We just use the Rubin boundary condition to approximate the Dirichlet boundary condition. Here we add this term, the normal derivative term. Here delta is that small parameter. We know that as delta goes to 0, this Rubin boundary condition can approximate the original Dirichlet boundary condition, right? Then this Rubin boundary condition, we can solve the normal derivatives. Also, we do not know the explicit value of the normal derivatives. We can solve the normal derivatives using U and just replace this normal derivatives into the original integral approximation. We can get this nonlocal model. Right? This is very, very simple, very simple. Just use the Rubin boundary condition to approximate the original Dirichlet boundary condition. We can also prove that the convergence rate is square root of delta. Square root of delta. But then also still have some problem of this nonlocal formulation. One big problem is that this model does not symmetric. Is not symmetric. Is not symmetric. This term is not symmetric, actually. So which means that if we want to solve it numerically, if delta is very small, because we want to approximate the Dirichlet boundary condition, we need the delta is small. But when delta is small, this after discretization, we can get a linear system. But the coefficient matrix of that linear system is actually not very good, especially when delta is small. It's not very easy to solve it. In some cases, it is even ill condition. Okay. So then we have another improvement of this this model. The problem is that we need the delta is small. Then the numerical method to solve this nonlocal model is difficult. The other approach, I forgot to mention that we applied this nonlocal model into so-called low-dimensional manifold model in image processing, and we can get a very good result in the image imprinting problem in many for different kind of image. This is a natural image, and this is actually the solution of the plasma equations, and this is the image of some biological tissue. Okay, for different kind of image, we can got a very we can get a very good example, good result. However, but in that model, we need to solve that integral equation with a small delta, which may be difficult in numerical sense. The other idea is that we first we transform the original Dirichlet problem into this optimization problem. It's a very standard, right? In the textbook, even in the textbook. Then we use the boundary condition is here in this constraint. It's of this constraint in the optimization problem. Then we can use so-called augmented Lagrange multiply method to handle this constraint. This is a standard augmented Lagrange multiply method. They just solve this constrained optimization problem iteratively. And in each step, we only need to solve unconstrained optimization problem. It is a very standard method in optimization. And if we use that augmented Lagrange method on our problem, we can get that in each step, we need to solve this unconstrained optimization problem. Here, mu is a fixed parameter. It can be 1, actually. It's a fixed parameter. Okay, if we use a standard versional approach, this optimization problem can be rewritten into this PDE model. It is also a Poisson equation with Robin boundary condition, which means that in each step, we need to solve this Robin problem. Oh, here, we also need to solve a Robin problem. But the point is that here, the parameter mu is a fixed number, not a small or large number. Not a small, it can be 1. It can be 1. So this is the final algorithm. You need to solve this Robin problem iteratively to impose with a fixed parameter to impose the original Dirichlet boundary conditions. Okay, of course you can discretize this integral equation on point cloud. Just replace the integral by summations over the points. In point cloud, if the point is if you have mesh, you can also use in finite element method to solve it. Actually the convergence rate of our nonlocal model is much lower than the finite element method. With good mesh. But if you do not have good mesh, if the mesh is poor, then you cannot get any convergence with the finite element method. But our nonlocal model can still get some reasonable solutions. Okay. This is another approach to impose the Dirichlet boundary condition. However, theoretically, that approach is not symmetric, neither, because you use a Robin boundary condition to approximate the original Dirichlet boundary condition. The integral equation is not symmetric. Can we get a symmetric nonlocal model? Because the original local model is symmetric. So we want to preserve that structure to get a nonlocal model also has symmetry. Okay, then the idea is as following. We can use the integral approximation on the interior domain and also on the boundary. We can get these two integral equations. But this system of integral equations is not symmetric neither. However, we can modify this integral equations a little bit to get a symmetry. The modification is here. To preserve the symmetry, we need to here the kernel function. We need to use replace the original R by R bar to get a symmetry with this term. And correspondingly, we need to replace this kernel function by R bar, a double bar. A double bar is actually a primitive function of R bar. And also here, the kernel function is also R double bar. This integral equations are symmetric. Is symmetric. Okay. Further, we also to get the coercivity, we also modify the second term here, the second term a little bit. We just here, we just replace the R variable, Y variable by X. then we can put this term, normal derivative term out of the integral. Then we can easily get the coercivity of this integral system. And here, in this system, we treat normal derivatives of u as an auxiliary variable. Actually, in this system, in this model, we solve u, the solution u, and the normal derivatives together simultaneously. Okay. And based on this observation, we can get a non-local model in this form, a little bit complicated, but the idea is very simple. It's just based on the previous ideas. And this non-local model has a variational form, can be written associated with this energy function, which means that it is symmetric. And this energy function is also coercive. Then the Wellposedness of that non-local model can be proved straightforwardly using standard Lax-Milgram theorem. And we can also get the convergence as delta goes to 0. The convergence in H1 norm is, for this model, is of the order of delta, a little bit higher than the original, the previous non-local model. Due to it, since it has some good symmetry property. Okay. However, this model, although it is symmetric, but the convergence rate is of the first order. Actually, for the non-local model, the optimal in the interior area, if we do not have the boundary condition. For example, if the boundary condition is a periodic boundary condition, then it is very easy to check that the convergence rate is a second order. Is of the second order. So here with the Dirichlet boundary condition, we also want to get a non-local model of the second order convergence. But for this model, we can only get a first order convergence. Can we get a second order convergence model? The answer is yes. To get a second order convergence model, we need to go back to the error of the original integral approximation. Actually, the leading order term of that the error is this boundary term. This boundary term. It is not small near the boundary. This is the leading order term. To get a high order non-local model, we need to handle this error term, this boundary term. How to handle this boundary term? But in this boundary term, there is second order derivatives. This is actually the Hessian matrix of the function u. The idea is to decompose this boundary term to normal direction and tangential direction. We can decompose here x minus y, this vector to normal direction and tangential direction. This tangential term, this term is actually small because in the tangential direction there are some cancellation. This integral, we have some cancellation, and actually this term is of the order of delta. This term, the normal term, is order 1. Then we need to handle this normal term. How to do that? Actually, this term, this normal, this is a Hessian matrix in the normal direction can be written in this form. It is just the trace of the Hessian matrix, which is the Laplacian operator. Laplacian u minus the Hessian matrix in the tangential direction. However, because we know we know with the Dirichlet boundary condition, we know value of u in the boundary. So we can compute this tangential derivatives. We can actually compute the tangential derivatives. Under this term, actually, after careful calculation, we also have a first order term, which is a normal derivative, and this kappa is a curvature, Gaussian curvature of the boundary. Okay, now the Laplacian u is known because we have the Poisson equation. We know the value of Laplacian u, and then we can, using this approach, we can handle the boundary term, and we can get this very complicated non-local models. And now we can prove that the convergence is of the second order. Okay. This is the idea of the second order non-local model. Okay. Now let's go to another approach. This model seems to be perfect, which is the second order, which is optimal. Second order is the optimal order for non-local model. It is symmetric also. However, it does not preserve another important property of the original Laplacian operator, which is so-called the maximum principle. This non-local model does not have maximum principle. Can we get the non-local models, which is symmetric, also preserve maximum principle? Okay, this is the models we will introduce later. Okay, the idea, let's go back to the original Rubin approximation. We get this integral model. However, this model is not symmetric and does not preserve maximum principle neither, which seems to be very bad. But if we just modify this model a little bit, we can get a model which is symmetric and also preserve maximum principle. We just replace here the y by x. Then this model is symmetric and also preserve maximum principle. Okay. As a maximum principle, we mean that for this integral operator, it is very easy to prove that we have this so-called maximum principle. If this is greater than 0, then this function is also greater than 0. And consequently, we can so-called comparison principle also. And use this maximum principle, we can prove that this model has a first order convergence in L infinity norm. Because we prove that in the with maximum principle, so we can go the pointwise convergence. Okay, I don't know. Okay, let's just give a sketch of that proof. Very simple, very brief sketch of the proof. If we denote here, E delta is the error. U delta is the solution of the non-local model, and U is the solution of the original Poisson equations. We can show that this one, L delta, E delta, is controlled, is bounded by this term. By some local truncation error analysis, we can prove this bound. And on the other hand, if we choose V as the solution of this problem, we can show that L delta V is greater than this term. if you compare these two terms and using so-called comparison principle, using this comparison principle, you can easily get this error estimate. Because this term, this term is actually smaller than delta times this term, right? Because this term is actually order 1, and yeah, this term is we can prove the first order convergence. Okay. However, this model is symmetric, also has a maximum principle, but it only has a first order convergence. So we know that the optimal convergence rate is second order. So we want to improve this model further to get a second order convergence model. Also symmetric and has a maximum principle. Can we do that? The answer is also yes. The idea is that we modify this parameter, this delta, a little bit. Here, delta is a constant over the whole domain. Then we can replace this constant by a function of x. We just replace that constant by this function. Here, d is just the distance of x to the boundary. This function is just if x is far from the boundary, larger than delta, then it is just 2 delta. It's larger than 2 delta, then this beta is equal to 2 delta. If d is between 2 delta and delta square, then it is just d. If d is smaller than delta square, then it is just delta square. Okay, this is the choice of that parameter. If you replace the constant by this function, then we can prove that this nonlocal model is of second order. The key point is that with this variable parameter, we can prove that this error term is bounded by this term. And V is also here. V is also the solution of that Poisson equations. We can prove that it has this lower bound. Then this bound, this upper bound and this lower bound has a second order difference. In scale, the difference is of second order. So we can prove that this model has second order convergence, which seems to be perfect, which is symmetric, has maximum principle, and also has optimal convergence rate. Actually, this is the final model we have now. And the last one I want to mention that these two terms also have this equivalent variational form, which means that it is symmetric. And using this variational form, we can easily prove the Wellposedness of that nonlocal model. Okay, we can actually, this nonlocal model is very easy to implement, especially for this first order model. It is very easy to implement, and it's very easy to solve, because this model is symmetric, and if we discretize it over the point cloud, the coefficient matrix is also positive definite. It is very easy to solve. Okay, we find that it is actually very closely related to the so-called weighted nonlocal Laplacian we proposed several years ago. It has a very good result over the semi-supervised learning problem, especially when the label rate is lower. For example, in this MNIST dataset, it totally has 70,000 images. And if we only label 100 image in this data set, then the accuracy we get can be larger than 90%. But if you do not if we use the standard graph Laplacian, which are introduced at the beginning of this talk, the accuracy is actually much lower. Okay. Finally, let's go to another. Let's put this discussion of the nonlocal model to another direction. In the previous part, we just improve the nonlocal model further to get a very good nonlocal model. But to get that very good nonlocal model, we need to very carefully design the kernel functions. Right? So the other direction is as following. If intuitively, we can impose the boundary condition, Dirichlet boundary condition, using this penalty term. And actually, the previous nonlocal model can be written in this form also. But in that kind of nonlocal model, the kernel functions R delta and K delta are very carefully designed to get that good property. Then the other question is that for what kind of kernel functions we can get the convergence? We want to relax the conditions on the kernel functions to see the limitation, the boundary on the other direction. Right? So, but if R and K are just general kernel functions, we cannot get so strong convergence. In H1 norm, in our infinite norm, we cannot get so strong convergence. Then we just analyze the convergence in gamma convergence, in the sense of gamma convergence. Gamma convergence actually is much weaker than the convergence in norm. We can prove that with very mild assumption or requirement on the kernel function. We can prove that this penalty model actually converge to the original local model in gamma convergence. Okay, this is another discussion. This is a discussion on another direction of this nonlocal model. Okay, at last, let's make some conclusion. In this talk, I just introduced many different kind of nonlocal models. We just use, first we use a Rubin approximation to get two nonlocal models. And then we introduce some symmetric nonlocal models. Then we introduce the nonlocal models has maximum principles. And at the last, I discuss the general penalty models. In the future, there are some works still ongoing. For example, we want to generalize this method to other problems. For example, Stokes equations, by harmonic equations, and interface problem, and local-nonlocal coupling problem. Here, I just want to mention that recently we just found that the interface problem is very powerful, very effective in semi-supervised learning problem. It is actually not surprising because in semi-supervised learning problem, the function we want to get is just the label functions, which is a piecewise constant, actually. For example, for the classification problem, that label function should be 1 at this class and 0 on the other class. It's actually, this is a typical solution of the interface problem. The interface is actually the boundary of that class, of each class. So the interface problem is actually very effective for the semi-supervised learning problem, especially when the label rate is very, very low. Recently, we get some results for example, in that MNIST data set. If we only label 1 point in each class, only 1 label point in each class, we can also get the accuracy higher than 90% using this interface model. Okay, this is one result. One recent, we are still working on this problem, and hopefully we can put we can write we can complete the paper in a couple of months. And okay, then the other problem we are working on is to develop a second high order non-local model with Neumann boundary conditions. As I mentioned earlier, the Neumann boundary condition is natural in non-local models. But in that way, you can only get the non-local model with first order convergence. Because the reason is also that the boundary term, of the second order derivative is only the first order. It's the limitation of to get a high order non-local model. So now we are just working on to run the second order non-local models with a Neumann boundary condition. Okay, we also want to develop some so-called ACE numerical schemes for these non-local models. Okay, here are some references, and thank you.
Many thanks to the speaker. Any question or comments?
Oh, okay. Yeah, because in graph Laplacian model, the boundary condition of the labeled value is not correctly imposed from the numerical PDE point of view. Yeah. Yes, yes. Okay, we have one example. This is the 1D tau example. We can say that, okay, sorry. If we use graph Laplacian to compute, there are some jumps on the labeled points. And for the MNIST classification problem, we can say that using the graph Laplacian, the accuracy is much lower than our non-local model, especially when the label rate is lower. When the label rate is high, actually there are no difference between these two models. Yeah. Yeah, because it's a one-dimensional problem. Yeah, the boundary, if in two-dimensional, the boundary is a curve, closed curve, right? Yeah. Yeah. Yeah, exactly. Our model is actually just the adjusting the weight. Yeah, yeah. Put more weight on the label points. Yeah. Yeah. In practice, in the thermal superposition problem, we just treat delta as a label rate. Oh, okay.
Thanks for the question. Any more questions?
Uh, uh, we did some research on the problem that the manifold on the or the computational domain is given by some random points. Yeah, the point cloud, actually the point cloud is a randomly sampled points, not a structure grid points. We did some kind of we did that kind of analysis. We have some results on that. But for another different, I don't know what kind of randomness you want to do. Oh, yeah, the stability, if you perturb the manifold or the point cloud, the stability to that perturbation is actually very difficult to analyze, I think.
Thank you for your question. Okay, I think, one more question.
So in principle, the dimension is actually the dimension of your data. Because if you are in graph, you do not have any dimension information. Amnesty pixel, the dimension is that 784. Yeah. Yeah. We just treat. It's not rigorous. It's not rigorous. We just treat the labeled point as the discretization of the boundary. Yeah. 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 But it's not rigorous.
Okay.
Sorry, what can you repeat your question? I'm not very familiar to the engineer application of the nonlocal model, but as talked by Professor Qiang Du and also Professor Zhou, there are many applications in the so-called barodynamics. And for example, smooth particle hydrodynamics is very popular in the computation of fluid mechanics, I think. Yeah, I'm not very familiar with this kind of applications. Sorry about that.
Okay, because of time, we can discuss with speaker personally. Let's thank the speaker again. And the next talk will begin at 11 o'clock. We can have a small break.